So welcome to the IAMP seminar today. So today it's our pleasure to have as a speaker Wei-Min Wang from CNRS and the University of Cergy in Paris, and she will talk about the dynamics of nonlinear, random, and quasi-periodic systems.
Okay, well, thank you, Margarita, for the introduction. And so today I want to talk about both the random and quasi-periodic systems. So one of the main problems in condensed matter physics, and also more recently, I guess, quantum complexity theory, is to understand the eigenstates of local Hamiltonians, right? They describe the physical state of maybe what you can observe. So disorder-induced localization. So we'll make more precise what disorder means. So this is usually AKA attribute to Anderson localization, it's called, was introduced by Philip Anderson, right? You probably all know who Philip Anderson was. Won the Nobel Prize in 1958, okay. And he suggested a mechanism responsible for the absence of diffusion of waves in disordered media. I do not know if some of you might have looked at his paper, original paper. It's quite amazing with lots of diagrams. So he suggested a mechanism for the absence of diffusion. So the idea is that you have a metal, and the idea is that when you have the metal there's too much dirt in the metal, that the metal ceases to conduct. Now, I mean, this is called Anderson localization. Now we are no longer shocked by it, but at the time people were shocked, right? You're given a metal, it conducts. What do you mean it'll stop, right? Okay. So now this mechanism is well understood by now in the single particle case. So I think Anderson, yeah, in that paper, it might be just one particle, but he might also have mentioned that, it's not just one particle. So both physically, so that was Anderson, and mathematically also. To begin with, Anderson said, well, you have all these disorder. Since we do not know much about them, we just take them to be random. Okay, this is the reasonable first step. So this out came the random Schrödinger operator, and the localization manifests itself as pure point spectrum. So the spectrum has only eigenvalues, as you know that the spectrum can have continuous spectrum, right? With the corresponding eigenvectors exhibiting exponentially fast spatial decay. I'm not very good with iPad, but anyway, you have a bump function essentially, okay? So imagine that. For almost all configurations of the environment. So pure point spectrum, you only have eigenvalues, and if the metal conducts, then it has continuous spectrum. Okay, so this is roughly the idea. And the eigenvectors decay exponentially, so it cannot go, the electron cannot go very far. Oh, I'm skipping. So this is one way of mimic disorder, but it's not the only way. Another way to mimic disorder is to take quasi-periodic potentials. So what does it mean, quasi-periodic? I think it's maybe a bit less known, although it's also quite well known. For example, quasi-periodic potentials can model crystals with defects, right? We know crystals have a periodic structure, and what if it's not quite perfect? So then it's called quasi-periodic. For example, after I gave the slides, this is when I start to revise just tiny little bit. So I gave an example in one variable. If you take the function, the potential cosine x plus cosine alpha x, x in R, or simply cosine f alpha x if x is on z, then this is quasi-periodic when alpha is rational, because this guy has period 1, and this guy has period, I guess it's 1 over alpha, and they are not commensurate. So you have two incommensurate frequencies, and you lead to quasi-periodic potentials. And this is quasi-periodic on the lattice because lattice has spacing 1, that the 1 is already intrinsically there. So here's a precise example of a non-random potential which can also model the defects, disorder. There is an analogous formulation of a localization in the quasi-periodic case. Although, as you see a bit later, the situation is a bit more delicate in the quasi-periodic case. Okay, so you also have the notion of localization that you have, pure point spectrum with exponentially decaying eigenfunctions. You have these bump functions. Okay, so all of this is very good. One particle quantum mechanics, right? It's beautiful. However, there is a lack in this one particle picture as there are interactions among the particles. I mean, Anderson obviously realized this. Later he did more work on this. This leads to a many-body problem. And as we all know, many-body problems are very hard. As an approximation, one may look at effective nonlinear equations. Okay, this is how nonlinearity comes in, right? The nonlinear term is used to model or mimic the many-body interactions. I think probably we probably all know a bit of this or have heard of this. Okay, so the nonlinear difference equation. This talk will mainly discuss nonlinear difference equations on the lattice ZD. Okay. For example, we have the nonlinear Schrodinger equation. So without this term, it's your good old Schrodinger, linear Schrodinger equation. Then you have added this nonlinear term, right? Here, it's all linear, but here this comes in a nonlinear way. And you can also consider the nonlinear wave equation. The nonlinear wave equation, the same on the right-hand side, but the left-hand side, I dt is replaced by d squared dt squared, right? So this is more, I think this is classical, described like oscillators, or a string of particles, classical. So one way of seeing this, there are some precise results. I mean, U2P is seen as particle density, right? So U is the particle wave interacting with the wave density. So it's modeling interparticle interactions. Here, U is interacting with the potential, right? This is the mean field, and you go, next step, you have this term. Is it called Hartree Fock or various names? This is an approximation. So let's go back, right? The delta and epsilon parameters, they are in 0 and 1. Laplacian is the usual lattice Laplacian nearest neighbor. So I think you know this, right? You take the potential, the wave function site x in one dimension one, so the Laplacian x will be, Laplacian u will be you take the right-hand side neighbor, left-hand side neighbor. Okay. You generalize to higher dimension to just nearest neighbor. And v is the potential. So in the discrete case, it's easy to formulate. It's just a family of random IID random variables indexed by ZD, right? This is easy now. J lives on ZD, and V is a random variable. So imagine yourself, each side of the lattice, you have a random variable. So you have a whole family of random variables, IID random variables. And with bounded nice distributions, right? These random variable has a distribution. And I do not want to play with this. If you're a big specialist of Anderson localization, there are all sorts of distributions you can take, but I take it nice. All V is a quasi-periodic potential. So like the one I mentioned. Where's the quasi-periodic potential? Yeah, or V, you can take this instead of a family of IID random variables. And so in particular, the difference is that in the quasi-periodic case, it's a deterministic potential, right? You can write down the form of the potential. In the random case, well, you're given a distribution. You do not know how the function looks like, right? It's a realization potential. The nonlinear, okay, so since I'll be talking about mainly about nonlinear problem, the nonlinear random case has a longer history, slightly longer. The quasi-periodic case is a more recent development, but as we'll see, however, the phenomena in the random case does extend to the quasi-periodic one, at least in the problems that I and my collaborators look at. I mean, a priori, this is not obvious because one is deterministic with infinite number of parameters, right? Each random variable is parameter. In the quasi-periodic case, well, for the example, cosine x plus cosine alpha x, the most you have is the parameter alpha, just one. But for certain problems, they seem to have share similar properties. So this is what I want to touch on today. Okay, so let us start with the random case. So we start from the linear problem. So we have the linear operator. V is random here. It's a family of IID random variables. And the linear Schrodinger equation is with the U, right? This operator operates on U, then you have IDDT. So there are two cases. One is arbitrary D. So if epsilon is very small, that is the Laplacian, the coefficient in front of Laplacian very small, H has Anderson localization. So this dates from the fundamental work of Friedrich Spencer in 1983. And there's a version by von Dreyfus-Klein, and then a bit later by Eisenman-Molchanov. So what they proved is namely the spectrum of H is pure point with exponentially localized eigenfunctions. So this is what I said, and this is what they proved, okay? And each eigenfunction 5j is localized about some point Lj and has rapid exponential decay away from it. Okay, I'm speaking this way, but there's always with certain probability or with probability 1, okay, that I'm not repeating now, okay? We do have this bump picture. That's so that's proven mathematically. Now there's okay, so before that was just the property of the Schrodinger operator. Now the dynamical consequence means that we look at the Schrodinger equation. So you look at, you're putting I ddt to the left-hand side. Okay, because of separation of variable, we can do eigenfunction decomposition, right? This is the point, okay? But the right-hand side, I guess I do not need to go back, doesn't have t dependence. So you have separation of variables of t and x. Okay. So dynamical consequence is given any initial condition u0, which you take cj, phi j, you have a linear superposition, right? Phi j are the eigenfunctions, and you take a localized about the origins. So let me just stay at this level and not be too quantitative, okay? Just, a combination of bump functions. And let mu j be the eigenvalue for phi j. Then the solutions to the random Schrodinger equation is just this, right? You operate on I ddt, you just get this vector. You just plug it in and you get it, and you see that it's localized about the origin for all time because the phi j's are localized. This just introduces the phase. This is the linear. And the third property, the solutions are almost periodic in time. Why do I have trouble with the keys, actually? Almost periodic, you see, if you only take one eigenfunction, this is periodic, right? With the period depends on mu j. If you take two, again, they might not be commensurate. They might be mutually irrational, then you have two frequencies, so it's already not periodic in time. And almost periodic just means that you could have infinite number of periods. Okay, so it's almost periodic. Oh, sorry, I'm having trouble with the solutions are almost periodic in time. So the linear problem, the solutions are almost periodic in time. This is what we should remember. But here we should note, I said the spectrum is pure point, right? It only has eigenvalues. But the spectrum is dense pure point. So to fix ideas, you can think of the spectrum consists of all rational numbers. Okay, it's pure point, right? But it's dense. So this is the situation of a linear random Schrodinger operator spectrum when you have localization. So it's a complicated situation, actually. And then in the other case, d equals to 1. In one dimension, one may take epsilon equal to 1, right? Any finite epsilon fine. And there's also Anderson localization, and you have what's called dynamical localization. If you take a wave packet near the origin, it remains near the origin forever, and that the solutions are almost periodic. The Lyapunov exponent is strictly positive, so this follows famous work of Furstenberg. It's also a subject in probability, and Gosheim, Ochana, Pastou, and there are some more recent work by these authors. So it has recently there are more activity on the subject in the last 5 years. Now, so that's the linear situation. Now we turn to the nonlinear random Schrodinger equation. Turning to the nonlinear equation of ZD when V is random, it is so. So far I've talked about equation without this term. Now add this term. When V is random, it is natural to ask what happens to the dynamics in the presence of the nonlinear term, right? I add this term, what happens? Among the nonlinear questions, there are the following two questions. Are there still solutions which are localized in space and almost periodic or quasi-periodic in time? This is like the linear case, okay? Do we still have, for the nonlinear equation, solutions like the linear solution? Number two, what about solutions to Cauchy problems? For example, for general initial data in L2, right? That's the other natural one because, for the linear problem, these two questions coincide. You work in L2 in any case. But as we'll see, these two questions entail different techniques in the nonlinear context. Okay. But these are the two natural questions, right? Do we still have, motivated by linear problems, do we still have such linear phenomena, essentially? So let's address question one. Are there still quasi-space localized time quasi-periodic solutions, right? We look for quasi-periodic in time. Okay, here I also mentioned quasi-periodic in space, but I have not brought that up yet, okay? In time, it's quasi-periodic. You saw that with the Fourier exponential I mu jt. And localizing space, right? Because it's Anderson localized to the non-linear random Schrodinger equation. In other words, do we still have Anderson localized solutions to the nonlinear problem? Again, we consider two cases, arbitrary d, small epsilon, small delta, and d equals to 1, epsilon equal to 1, and delta small. Delta is always small, okay? We want to see how much the linear situation extends to the nonlinear situation. So delta is always small, but epsilon is arbitrarily d, and epsilon is 1 in dimension 1. Oh. So let's first discuss case A, which is the arbitrary dimension case. And in this case, both epsilon delta are small. And we consider epsilon delta as perturbations to this equation, right? And this one is easy because Vj's are just sitting on the diagonal. The solutions to the above equation are just of this form with the frequency, the random variables, Vj, with appropriate conditions are Aj as j goes to infinity. So now we are going to take a finite, you remember for the nonlinear problem, you can take infinite linear combinations. Now for the nonlinear problem, we are going to specialize to finite linear combinations, okay? For the nonlinear problem. Finite but arbitrary, number of j's. And denote this number by b. We look for solutions to nonlinear equation near u0, treating both epsilon delta u and the nonlinear term as perturbations. So u0 is of this form, right? This is the linear Schrodinger equation. With omega j equal to Vj, this is an answer. As an ansatz, we look for solution to the nonlinear equation in this form. Okay, Aj is the same j here, right? Omega becomes n dot omega. Delta j is to delta j. So omega is omega 1, omega 2, omega b. Remember that we take b linear superpositions of the linear solution. Okay, these are the b basic frequencies. So the main difference, as you see, is that we have this n. So let me explain the notation in the ansatz. U0 is of this form, right? Remember, we start from an equation with just potential and no other terms, right? The right-hand side. So ut is of this form. So we can explain the notation this way. We write v equals v1, v2, vb as a b vector. Then v1, right? J runs from 1 to b, can be written as v dot e1. E1 is this. It just, the basis. So u0 may be written this way, right? It's ej dot v. And satisfy a and j equal to aj if n equals to minus ej and 0 otherwise. So it only has the base frequency. The linear solution u0 is localizing space, and there are only the base harmonics n such that n equals to 1, right? In the nonlinear solution ut, however, a priori, n may be greater than 1. Okay, this is the main difference, one of the main difference. These are the higher harmonics of the basic frequencies. So in the nonlinear problem, not only you have the base frequency, you have higher harmonics of the basic frequency. This is a main difference with the linear solutions. Why? Because the nonlinear term, you see, when you u2pu has exponential I vt, and you take powers of it, you have higher harmonics, right? This is, yeah, you have a multiplication, and in the exponent, it adds. So you have higher harmonics. So this is the main difference with the linear equation. So this is why we take, for the ansatz, there is an n, the higher harmonics. You have to control the higher harmonics. Of course, higher harmonics have higher energy, right? That's one of the difficulty of nonlinear problem. Energy can increase. Okay, so putting it in words. So the question is, do we still have Anderson localized solutions for the nonlinear problem? When you take your close to, finite linear combinations of linear solution, close to it. Putting it words, our theorem with Boga will say that there is an abundance of such solutions, UT, the solutions that I just flashed on the screen, which are quasi-periodic in time and localizing space to the nonlinear equation as well. And moreover, they are close to U0. Okay? A priori, this is not obvious because the higher harmonics can, bring you to very high energy. Things might not be well defined. So indeed, Anderson localization can persist under certain conditions. So let me more precisely. So let me skip the next slides. These are more precise statement. Okay, there's a large set such that you can continue Anderson localized solutions. Let's just put it that way. So that's the result with Boga in 2008 for the random Schrodinger operator, nonlinear random Schrodinger equation, arbitrary dimension D. And I like to mention that recently the paper with these co-authors, we improved on the result in this result. Okay. And case B, how about dimension 1? In dimension 1, epsilon equals to 1, you still have linear Anderson localization. So what about if you make a small nonlinear perturbation? Do you still have such solution? Same question. Now, this is a recent work with Liu Wencai. The main difficulty and the difference with the arbitrary dimension case is that when epsilon equals to 1, one may no longer treat the epsilon delta term as perturbation, obviously, right? We cannot start with the equation with the potential sitting on the diagonal, and that's it. We cannot. Consequently, one may no longer use the canonical basis for L2Z, right? Instead, one needs to use the eigenfunction basis. It's obvious because you cannot forget epsilon delta. However, the eigenfunctions of the random Schrodinger operator are not, and in fact, cannot be known exactly. It's not possible. It was shown by already in the large disorder cases, now shown by Abel Klein and Elga. You cannot know it exactly. These are random variables. The linear analysis becomes more involved and leans on the state-of-the-art properties of linear Anderson localization. Okay, you cannot know them exactly. Again, we showed that there is an abundance of space-localized time quasi-periodic solutions. Okay, here I want to make a remark. The method in the work with Liu is robust, and in particular, it's also applicable to the nonlinear random wave equation. So it's the same co-authors. This is a work in progress. So summarize in the nonlinear for the random Schrodinger equation, one could continue the linear solution to the nonlinear equation under certain conditions. Okay, so this is the conclusion essentially. And here, the connection with many-body localization, which I alluded to earlier, is that the nonlinear random Schrodinger can be seen as an effective equation, right? To approximate many-body localization. And so there's this good review paper, many-body MBL. As is well known, right? One of the main difficulties in MBL is to control localization uniformly with respect to the number of particles. This is the difficulty. If you stop at 1 million particle, you still can't do a lot of, but it needs to be uniform with the number of particles. From this point of view, our theorem says that uniform in the number of particles, there is indeed an abundance of localized finite number particle states, okay, to the same degree of approximation. Such states do exist. So question number 2, what about L2 theory, right? Because before we consider time quasi-periodic solution, how about more general L2 theory, Cauchy problems? Right? For the linear problem, it's you have that too. So in one dimension, same problem. In one dimension, the work with Zhang in 2009, we show that when epsilon delta is small, an appropriately defined tail remains small for polynomial long time for any L2 datum. So you have L2 function, which also decays, right, eventually. And so you define the small part as a tail, and then you show that this tail remains small for a very long time. Polynomially long in epsilon delta inverse powers, okay? Not infinite time, but very long time. So there's long time Anderson localization for the nonlinear random Schrodinger in L2. For general data, we can only see long time. We cannot reach infinite time. But so there's more generality, but the time is limited. Okay, even though it's very long, it's limited. It's not infinite time. And so, but the thing is, this is the same space as L2, right? As for the linear random Schrodinger. Okay. So the proof uses, so now I talk about the L2 thing, long time Anderson localization. The proof uses Berkhoff normal form transform. So it's a coordinate transformation, right? Because to begin with, if you have epsilon delta, it's not diagonal. You try to diagonalize the matrix. This is what it does. And this method was initiated in the work with Bourgain in 2007 for a related equation. And this result has been improved to longer than polynomial timing in these three authors' work. So there is indeed very long time Anderson localization, but infinite time, we do not know how to do it. It's a difficult problem. Okay, now I want to turn to the quasi-periodic case. Okay, so I talked about the random case. So it's same equation on ZD, but V now is an arbitrary trigonometric polynomial. So it's not just cosine, it's a trigonometric polynomial, let's say, of cosine. In D variables, okay? In D-dimensional space, we have D variable, 1, 2, etc. D. So instead of a family indexed by ZD of IID random variables, we have a deterministic potential, which is a trigonometric polynomial in D variables. Okay, so we change the potential. Now, when delta equal to 0, this is the linear case. Bourgain proved that for any fixed theta 1, theta 2, theta d, okay, so let me determine. This is called the phase, and alphas are called the frequency. Okay, you think of rotation. This is the phase, cosine theta. This is the phase. This is the frequency. When delta equal to 0, Bourgain proved that for any fixed phase, the linear operator has Anderson localization for small epsilon in arbitrary dimension D. So he did manage to prove this as for the random case on the large set for a large set of frequencies. So that's the Bourgain work in 2007. It was a difficult work. So there's in dimension 2, it was proven by Bourgain, Goldstein, Schlag earlier. And then more recent, there's a work of Zhitomirskaya, Liu, and Shi, 2020 in arbitrary dimension D. And in the linear case, the results hold more generally for analytic potentials V, okay? For the nonlinear case, I need to specialize to the trigonometric polynomial. Again, finite number of terms, arbitrary but finite number of terms. Okay, maybe you'll see why later. So here I want to make a remark. When D equals to 1 and V is the cosine function, H is called almost Matthew operator. It's like the potential I gave at the very beginning. As most of you may know, it's called almost, and it's much better understood in dimension 1. Note that contrary to the random case, quasi-periodic localization depends very sensitively on number theoretical properties of the frequency vector alpha. Okay, the rotation, right? If alpha is rational, it's periodic. If alpha irrational, it's not periodic. So it's already obvious there. It's very different. It also depends on the phase vector theta, rotation. In particular, higher dimensions are much more difficult. You think of rotation in higher dimensions, right? Instead of a circle. It's a different story. It is not enough just to have large disorder, i.e. small epsilon in the rotation in higher dimension is much more involved. And one may therefore also put the same two questions, right? Since Bourgain did prove that for large disorder, you have also quasi-periodic localization, arbitrary dimension D. So let's ask the same questions. Namely, one, existence of space localized time quasi-periodic solution. Can we extend? Do we still have this type of solution, the nonlinear case, as for the linear problem? And long time Anderson localization by general L2 data, right? So if you agree that we could ask such questions to in the random case, or maybe you also agree that we can also ask such questions in the quasi-periodic case. Okay, here. It is well established that for both questions, the two questions I mentioned, the Diophantine properties of eigenvalues of the linear problem, so meaning this, right? I said I take finite linear, remember, I take finite linear combinations. It's never zero. So n is just this vector, okay, n1 to nb. So this is called the Diophantine property of the eigenvalues omega 1, omega 2 to omega b. It is well established that for both questions, the Diophantine properties of eigenvalues of the linear problem play an essential role. Maybe you know this, maybe you have heard of this. If not, maybe you could accept. It's these linear combinations. This is okay, so let's just say why one should accept one. The reason that this is a generalization of eigenvalue spacing to finite linear combinations, right? If you only have n1 and n2, and you change if this n2 is minus, then you have eigenvalue spacing, right? Omega 1 minus omega 2. This, as we all know, eigenvalue spacing plays a big role in a linear problem. Now, for nonlinear problem, it's this generalization that plays an important role. And this is needed for nonlinear problem. And one can understand this because the nonlinear term brings in higher harmonics, right? Terms of this form. Okay, so you want to know how their relation, right? Because these, they're not arbitrary, they come from these nonlinear terms. They bring in higher harmonics, therefore, etc., you can see that such things might appear in the problem when you want to deal with nonlinear problems. Okay, so now the key is to bounce these guys from below. This is a key. For the random problem at high disorder, i.e. small epsilon, this can be readily established using independence of the random variables. Because the omegas are just the v's, they are IID random variables. Well, there's not many questions that are easier than this one, right? They are IID random variables. Okay. Using independence of the random variables, which are potentials Vj at different size j. In D equals to 1, and when epsilon equals to 1, you have to take the true eigenvalues. Well, this is already a lot of work. But we managed in the work with Liu using fine properties of Anderson localization. This is already a lot more work. They're not the IID random variables anymore, right? Now imagine when V is quasi-periodic. Even for large disorder, what you have to say is you have to replace the omega by the quasi-periodic potential at different sites. Well, why should you have such a lower bound? It's not a priori obvious. It's a given function. The nature of the problem is entirely different from even the case epsilon equals to 1. Why? Because there are many fewer parameters than there are eigenvalues. Because if we go back, well, the most parameter we have is with D variables, we have 2D parameters, right? You can use alpha 1 and theta 1 and alpha D, theta D as random as parameters. So you have 2D variables and you have to control, arbitrary number of eigenvalues. So the nature of the problem is entirely different. Note that in the d equals to epsilon equals to 1 random case, there are still the same number of parameters as eigenvalues, right? We still have infinite number of random variables, infinite number of exactly the same eigenvalues. It's just the combination of the random variables in the form of eigenvalues are much more complicated, okay? But in the quasi-periodic case, it's a totally different problem. So we use a so-called generalized Wronskian approach, and that's initiating the work with Schr for the cosine potential. And we extended this approach, as it turns out, is general and applicable to any multivariable trigonometric polynomials. So indeed, if you take a trigonometric polynomial in arbitrary number of variables and you take them at different sites, on a large set of frequency and phase, they are linearly independent. So we use a Wronskian approach. So once you have that, it's similar to the random problem, modulo some technical things. So you do have this Diophantine property for trigonometric polynomials. Okay. As a first application with Song and Schr in 2023, we proved that there is Anderson localization on the large set in the alpha theta for polynomially long time. So it's like in the random case. Once you have this Diophantine property for trigonometric polynomials, you can do quite a few things like in the random case. That's what I mean. So there is long-term Anderson localization for the nonlinear quasi-periodic Schrodinger equation in arbitrary dimension D. This is the key estimate, the lower bound of these linear combinations of eigenvalues. So now the Diophantine result in the work with Schr should also lead to the existence of space-localized quasi-periodic solutions, right? That's the other question we ask. This is work in progress. And once this is done, completely done, it should prove the analog of the Bourgain-Wang result in the Bourgain-Wang result was in the random case, and now we can prove the same result in the quasi-periodic case, or because of this Diophantine property of trigonometric polynomial potential at different sites that we're able to prove. Now, I want to turn briefly to the wave equation. Nonlinear quasi-periodic wave equation. I would like to mention that with Schr, the work with Schr in 2023, just half a year ago, we constructed space-localized time quasi-periodic solution to the nonlinear quasi-periodic. So when you replace the left-hand side by a second-order time operating T, we can do the same thing on ZD. When we did it only for the cosine potential at the time. But later, but in view of the more recent result, this result extends to all trigonometric polynomials. But here we were only able to take cosine potential in one variable at the time. But as it turns out, the idea was much more general. For this one, we already used Wronskian, but then you see that it extends to arbitrary number of variables and arbitrary trigonometric polynomials. Okay. So it works for the wave equation. For the nonlinear quasi-periodic Schrodinger in dimension 1, such results were previously known from the work of Geng Zhao in 2014 and also Yuan in 2014. Yeah. Somehow they use a more classical KAM approach. We use, let's say, the work with Bourgain, we use more Anderson localization type of approach to the nonlinear problem. The nonlinear quasi-periodic wave equation seem to have, however, to have remained open until the most recent work with Schr. Somehow, for the classical KM method, wave equation becomes very, very different from the Schrodinger equation. The second order operator is more difficult for the KM. For us, it's the same, essentially the same thing. Okay, but it's a technical point maybe. So let me conclude. To conclude the talk, let me summarize the general problematics that we've been discussing so far. One, we work on the lattice ZD, right? We look at difference equations. Two, the linear problem has Anderson localization. Three, the nonlinear term, remember, it's U to P. Because U is decaying space, the nonlinear term is a decaying space. Okay, this is an essential. The nonlinear term is decaying space. We investigate the persistence of linear phenomena, such as time quasi-periodic solutions. These are, by the way, global in time solutions, right? You can write the whole expression, you know exactly how it looks like. These are called special solutions. In the linear case, special solutions are general solutions, but for the nonlinear problem, there are solutions of this form, but there are many other solutions. And long-time Anderson localization in appropriate L2 sense, right? So the conclusion is that the nonlinear random and nonlinear quasi-periodic systems, they share similar dynamics. For these two questions I look at, I'm not saying they're always the same. So I mean, there's a kind of a general thing that, you know, the random problem and quasi-periodic problem should be similar. I mean, under, you know, modulo lots of subtleties, but indeed, in these cases, I see that for the nonlinear problem, for the two questions I look at, they share a similar dynamics. So as I said, the key is to get the Diophantine property in the quasi-periodic case, which we managed using a generalized Wronskian. Okay, so finally, I would like to mention that in a recent joint work with Ilya Kashkovsky and Liu, we have provided a general scheme to solve the nonlinear difference equation. So far I've been talking about nonlinear difference equation. So in that paper, we provided a general scheme with almost all the details included. So one can actually read it and try to see the method. And we use what's called the Lyapunov-Schmidt method. So you divide the equation into the nonlinear equation into two parts. So so I did not mention earlier the work we use for us, for starting with the work with Bourgain on nonlinear problems, we use the Lyapunov-Schmidt method, and instead of the KM method, and we use subsequently we use the Green's function approach. So it's related to Anderson localization method. I think this is what I have to say.
Thank you very much for the very nice talk. Okay, questions, comments? Maybe I have already a first question. When you were giving you're looking at the linear case, the non-linear case with random potential. You were giving a condition on V1, VB.
I give a condition of V1, VB. What do you mean?
Well, you said on a large enough set of
oh yeah. So let me show you the precise statement.
I mean, well, I guess I was a bit confused because you mean it's a finite number of you look at the random potential on a finite number of lattice points, or this V1, V2, VB, you mean it's a finite number of points, or there is a large set, right? Is it you're looking at a finite number of points, or you go to infinite volume? I mean, because you work in
No, you
ZD
go to
and
infinite volume. Okay, so oh yeah, you use with okay, so now I need to explain a bit the improvement then. Okay. So in the problem with the Bourgain, you remember you have V1, V2, VZD, right? It's all
yes.
these random variables. Now the problem with Bourgain is we fix all the random variable except B.
Ah.
And we
Mhm.
and we assume that all the random variables are fixed in the what's called, so that you have Anderson localization, okay? And we save these V potentials as parameters for the nonlinear problem.
Yeah.
Okay, so I mean, you
Mhm.
have potential realization, and for these B frequencies, we take them apart. The rest of them, we fix the rest of them where there's own Anderson localization. Okay, you just imagine you take away B frequencies for later use.
And you're saying it's enough to fix these B frequencies to control the nonlinearity, or?
No. We do not fix B frequency. We fix everything except these B frequencies.
Mhm.
And we use these B random variables for the nonlinear problem.
And that's enough.
That's enough. Okay, so this is in a way not quite natural. I see that's why you have this question.
Yeah,
And
so the others are fixed in such a way you have Anderson localization for the
that's
linear problem.
that's right. It's not quite natural, okay?
Mm-hmm.
But okay, now the improvement is probably it's can be understood more easily. The improvement is you have a random Schrodinger operator plus a nonlinear term, right?
Mm-hmm.
So the improvement that we fix a potential realization such that there's Anderson localization. Okay?
For the linear problem.
For the linear problem. Then
Okay.
we use the amplitude as parameters for the nonlinear problem. So for any fixed realization of Anderson localization, there's a large set of amplitudes so that we have nonlinear Anderson localized state.
I see.
Okay?
I
So
see.
this is
Okay.
the more natural statement.
Yeah.
And for the Bourgain work, you're saving precisely these V's for your random problem. So it's a bit harder to explain, but this is very clear. You fix the potential where you have Anderson localization, and for a large set of amplitude, you have nonlinear Anderson localized state. Okay, so this is what we know.
I see. So you build on the fact that you know already that you have for the linear case Anderson
That's right.
localization, and you're showing that the nonlinearity is not destroying it.
That's right. And in this problem, if you like, away from these B potential, you take out these B sites, you have Anderson localization, okay? And
Okay.
you've added the potential of these B sites, then you have nonlinear Anderson localized state. So it's harder to explain this result. It's not as natural.
And do you have any, I mean, apart from the parameter delta very small, do you need the form of, is it important that you have exactly that nonlinearity? You have this u to the power p?
Oh, I mean, P is
Is the
arbitrary.
power important?
It doesn't, it's no way. The important thing is there's a delta, small delta in front of it.
So you can take any p, the p is...
Yeah, P doesn't play a role. As if its delta is small, P doesn't play a role.
I see.
But anyway, the state of the matter is indeed, is this one says that you fix any end potential realization such as the Anderson localization, then there's a large set in the linear combination that you have nonlinear localized state. So I think this is probably the statement we would like in any case. So that's the improvement. And now now what I want to say today is essentially this result also holds in the quasi-periodic case.
I see.
You still have such, and a priori, I do not think it's obvious actually, but it seems to be true.
Mm-hmm. If you have, there are questions, please feel free to unmute yourself.
Yes, can I?
Yeah, sure.
Yeah, so you're discussing that sometimes this quasi-periodic case is similar to the random case, and the key property is this Diophantine property.
Yeah. The key.
Yeah, do you have like any intuition for this? I mean, as you said, this is not a priori obvious, and that's
No.
I would say very, very surprising. And even if I see this Diophantine condition, I do not see any connection with random thing. But
No, it's a you should, I mean, it should. Okay. So to begin with, I saw this thing for the cosine function in one variable. Then somehow everything, one day, I guess one day one works better and see that applies in general. Okay, so the idea is one should not see things this way. One should see this as n dot omega. One should see the dot product. So the key is omega depends on parameters alpha and theta, right?
Yes.
Okay, so the way to do this is true. I mean, it's not always true on a large set of alpha and theta, okay, right? So you just need to show that some derivative to a certain order is non-zero. Then you can move things, right? And then, so you go through this Wronskian approach. You show that, okay, so the idea, the Wronskian approach, you show that, so you take certain derivatives and you show that it spans the space. If it spans the space, and then if you take any vector, non-zero, the projection on one of the direction has to be non-zero, right? It's geometry. And then that just entails some derivative of certain order is non-zero always. And then your business, then you can do such estimates. I agree, a priori, it's not obvious. But anyway, the paper is on archive.
Okay.
The paper is on archive. So this is the idea. You should really see n dot omega.
But wait.
Yeah, you have a question?
Sorry, when you're writing this, you mean this has to be true for
This is
a large set of n, or for
no. For all n on a large set of, remember, omega depends on alpha and theta.
Mhm.
On a large set of alpha and theta.
and n is any point in z.
ZD. Yeah, n is ZD.
Hmm.
Okay, so the idea is that if you take a certain number of derivatives and you see that they span the space,
Hmm. Mhm.
okay, and that if that's the case, the projection of any non-zero vector on one of the direction has to be non-zero, has to be greater than something,
Hmm.
and that's the derivative of
Hmm.
this term, and then you're in business.
Mhm. And once you have this property, it's somehow similar to the random case. That is what you want to say. Mm.
I suppose, yeah. In the random case, it's too easy
Yeah.
to think.
Yes, yes,
think.
yes. Mhm.
But you think of, I mean, on
Yeah.
a large set, right? You just need
Yes.
some derivative to be
Right.
positive.
Mhm.
See, the point is, it
Mhm.
doesn't need to be the first derivative. You do not even know which derivative.
Okay.
And all you need is to finite order.
Hmm.
And this is why we can do it for trigonometric polynomials and not in the analytic case,
Hmm.
if you like. Because for trigonometric polynomials, the derivative you only need to take some finite order.
Okay, thank you.
Yeah, once you have that,
Hmm.
well, the random case is still more complicated, but this is always the key.
Hmm.
I mean, for random, it's too easy, right? You do not think of derivative. I don't know. Random is too easy when it's omega 1, omega 2. These are random variable. That's way too easy, right?
Mhm. Yeah, if no question can ask a much
Sure.
more. Yeah, so I want to ask a physicist question. So you said your motivation is many-body problem. And of course, I mean, getting this kind of nonlinear Schrodinger from many-body is, of course, non-trivial step, but probably if you work on like low-density gas with long-range interaction, then yeah, there should be a hope of getting something like this. So probably you can
Yeah.
show it in some. So does this analysis give you any hope or any idea of treating the many-body case of random Schrodinger?
I have not looked at it, I have to say. I've been working on nonlinear problems. I mean, earlier than many-body localization.
Yeah, it looked like. Yeah.
Yeah. No, then
Okay.
well,
Yeah.
but then I see there is this
Hmm.
there is one can have this interpretation.
Hmm. But I think this connection is very delicate and subtle. I don't want to go into many-body localization, but
Oh yeah. It
they
seems to
now
be very
believe that
hard. Yeah,
it's only in one dimension and so on. But anyway, yeah.
right.
Hmm.
Well, the thing is, I
Hmm.
think this connection probably could be made fairly precise
Hmm.
to the same degree where you have the connection between nonlinear problem, many-body localization. Yeah, many-body problem. This is probably, yeah, this statement probably could be made precise to that extent. But that's all I know. I do not know I know many-body localization is very hard.
Hmm.
And it's fascinating. I mean, localization is fascinating. So it entails a totally different phenomenon, right? You do not have thermalization, you do not have equilibrium. Well, anyway.
Yes, thank you.
Other questions? Comments? Complaints?
Sorry,
Okay, so no,
like,
I don't see any. I don't see any. So let's thank the speaker again, and we can stop the official part of the talk.
okay, well, thank you.
So now I will stop the recording.